So now this is the last topic that I'm going to take in this subject. So here the topic is, this topic is actually kind of not that much important, but still they can ask if they want to, right? Especially they can ask for a short answer question. Here basically what you're going to learn is to find the magnitude response and the phase response of a function. Okay, the step is very easy. So before going into the magnitude phase response, first let me tell you, we all know that for a complex number, right, if you take any complex number a plus jb, let a be a positive or a negative number, let b also be a positive or a negative number, and if a plus jb is a complex number, then we can represent this in terms of its polar form, that is r angle theta, right? This is the rectangular form. This is called as the polar form. So what in that case, you have already learned this, right? So what is R? R is the magnitude of the complex number. That is, R is equal to root of a square plus b square. That is, this is the magnitude of this complex number. Or in other words, we also say a plus jb. We say like that also, right? Magnitude of a plus jb is equal to root of a square plus b square. Now, next is the theta. So what is theta over here? Theta is nothing but the phase of the complex number. The phase. And how to find the phase? Finding the phase is very easy. Simply tan inverse of the imaginary number divided by the real number, that is tan inverse b by a. This is how we find the phase angle. Okay, so basically we already know that all network functions are actually having a complex frequency s. So therefore, just like how a complex number has a magnitude and a phase, the same way every network function has a magnitude response and a phase response. What is the magnitude response? Magnitude response is the graphical representation of magnitude versus the frequency. What is phase response? Phase response is the graphical representation of phase with respect to frequency. And which frequency are we talking about? I am talking about this frequency, the actual frequency, omega. We all know that S is a complex frequency, but I'm talking about the angular frequency omega. So the first step, what you do when you're trying to find the magnitude and the phase response, the first step what you do is you replace S. When you see f of s, when you see S anywhere in the function, you replace S with j omega. Simply replace S with j omega. Then what will happen is that the network function will look somewhat like a complex number or a ratio of complex numbers. Next, the next step what you do is, so this omega is what you call as the frequency. Okay, so this function now becomes a function of omega actually, right? This becomes a function of omega. This omega is what you call as the frequency. So next step what you do is you simply find the magnitude and the phase angle of this. How do you find the magnitude? That is, the way of finding magnitude is wherever you see any complex numbers inside that thing. Whenever you see a complex number means definitely there will be j omega is there, and of course there will be some other imaginary number and real number will also be there. So wherever you see a complex number, simply replace that complex number with its magnitude format. Like that you can find the magnitude. That's how we find the magnitude of f of s, or the magnitude of f of j omega. We're simply replacing every complex values in that equation with the magnitude form. Okay, that's how we find the magnitude. Okay, and then so this is nothing but a equation in terms of omega. So with that, looking at that equation, you can plot the graph for different values of omega. And then you go to find the phase angle. Phase angle also same step. After replacing every s with j omega, you can also find the phase angle using the equation theta is equal to tan inverse b by a. That is, wherever you see any value with j multiplied, that is the imaginary part, and any value without the j, that is the real part. So that means you just replace you put the imaginary part on the numerator and the real part of the denominator, and tan inverse of that will give you the phase angle. And this is also a function of omega. So therefore you can plot those values also for different values of omega, and that is called as the phase response. So this is how we mark the magnitude phase response. So let me show you, I'll just give you two problems on how to do this. Okay, then you'll have a general idea of how to do this portion. So here, for example, okay, one example I will give you. Let f of s, okay, is equal to s by s plus 10. Okay, This is how the question, they'll give you a simple function like this, okay? F of s is equal to s by s plus 10, okay? So first step what you do is you write like this, you replace s with j omega, okay? Because you want to express this in terms of its angular frequency. That's what you're trying to do. So f of j omega is equal to, so replace s, wherever you see s, replace it with j omega. So you have j omega over here, divide by j omega plus 10, okay? Or if you want, you can write like this also, j omega by 10 plus j omega, okay? This is it. See, you found it. Now next what you're going to do is that you're going to express this in terms of its magnitude. So magnitude means what is the magnitude of j omega and what is the magnitude of 10 plus j omega. What is the magnitude of j omega? We all know that the magnitude of a plus jb is root of a square plus b square, right? The magnitude of a plus jb is root of a square plus b square. In that case, what is the magnitude of j omega? The magnitude of j omega is nothing but, you see, how to write it? I'll write like this, okay? That is 0 plus j omega. What is the magnitude of 0 plus j omega is nothing but root of 0 square plus omega square, or it's nothing but omega itself, which means the magnitude of this is omega, okay? And what is the magnitude of the denominator? Here the magnitude of the denominator is root of a square plus b square, a square plus b square. So it is 10 square plus omega square, or you can also say it is nothing but omega by root of 100 plus omega square. See, so this is the magnitude of, or the equation for magnitude or magnitude response of f of s, of this function, okay? So what you do now is that you just simply plot the different values of omega onto a graph, okay? And usually the graph that we use is the semi-log graph. One of the properties of semi-log graph is that the distance between the powers of 10 are same. That is the thing. That is the distance between 0 to 10, then 10 square. So the distance between 10 to 100, the distance between 100 to 1000, the distance between 1000 to 10,000, and so forth. You see, the distance between every powers of 10 are the same. That is one of the properties of the semi-log graph. So we usually plot this magnitude response and phase response and the phase response onto the semi-log graph, okay? So here what you do here is, now we are going to plot the values of these values, okay? So for different values of omega. So if you want, you can use different values of omega, okay? So you see, so I'm going to say, I'm going to plot the value of omega over here. So we all know, right? Let me write the equation again. That is the magnitude response is f of j omega is equal to the value I got is omega by root of 100 plus omega square, 100 plus omega square. This is the equation I got, right? So this is the omega and this is the magnitude f of j omega, okay? So I will plot the values of omega in terms of how, in terms of 0, okay? Then I will find the value 5 hertz, then 10 hertz maybe, and after 10 hertz maybe I'll try for 50 hertz, then after that 100 hertz, then maybe 500 hertz, then maybe 1000 hertz. Let's see what the values you get, and based on these values you can plot the graph, okay? So the graph will look like this. That is, this is how the graph will be like. So that is, we have a vertical graph, a vertical line, we have the horizontal line over here. This is the y-axis represents the magnitude and the x-axis represents the frequency. This is called as the magnitude response. That is the graphical representation between the magnitude versus the frequency. So this is the values of different frequencies. So I'm going to substitute every values of omega over here, and I'm going to find the value of the magnitude over here. So the first value is 0. Yeah, of course, if I put 0 over here, it will become 0 by root of 100 plus 0, which is 0 itself, okay? So which means the first value over here is 0. Let me mark those values. So here in a semi-log graph, don't forget the distance between the powers of 10 are the same. So this is 10, this is 100, and this is 1000, okay? I'm not going to go greater than 1000, okay? If you want, you can go greater than 1000, no problem. We'll see how it looks like. So this is it. So here, I'm going to do is, I'm going to substitute the value of 5 over here and see what answer I'm get. So for that, I will say 5 divided by root of 100 plus 5 square, right? This is how it looks like. 5 divided by root of 100 plus 5 square, and I will get the value as 0.447. So this is 0.447. Okay. Next is 10. So to get 10, what I will do is I'll substitute this expression over here. It will become 10 divided by root of 100 plus 10 square. Right? 10 divided by root of 100 plus 10 square. What will the value will I get? Let me see. I will get 0.707. So this is 0.707. Okay. Next is 50. Okay. So I will substitute the value of 50 over here. So in that case, I will replace 50 divided by root of 100 plus 50 square, and I will get 0.98. Almost equal to 1, right? Almost equal to 1. 0.98. Okay. And what about 100? Let me see. For 100 divided by root of 100 plus 100 square, and you will get 0.995, which is almost equal to 1, right? Almost equal to 1. Okay, let me write 0.995. Next is I'm going to find 500. Okay, let me try 500. So 500 means I just replace the value over here with 500. So this is 500 divided by root of 100 plus 500 square, and I will get 0.998, which is nothing but 1. You can say 1 and say, oh yeah, right, 0.9998. Okay, almost equal to 1. So now last value is 1000. Let me put 1000 over here. So it will become 1000 divided by 100 plus 1000 square. You see, because as this value increases, the significance of this value decreases, right? That's why you are getting almost the numerator denominator is almost getting same. So you will get 0.49 and then 5, right? Which is almost equal to 1. Which means now if you go to this, now if you keep on increasing, the value just becomes more and more closer to 1. Which means the maximum value is 1. Which means if I have to draw the graph, right, it's easily understood. If I draw the graph, if this has to be 5, so 5 means 0.47. okay, that is, I'm going to mark it like this. Let this be 0.2, let this be 0.3, let this be 0.4, this is 0.5, 0.6, 0.7, 0.8, and we increase the size of the graph. This is 0.9 and this is 1. Okay, so which means if I'm going to draw a 0.447, which means somewhere over here. Okay, let me mark it, and you need to draw it in original graph, but here this is fine for me. So this is the point. Okay, this is first point. Next will be 10 is 0.707, which is somewhere over here. Okay, that's one over here. Next you have 50, which is 0.98, which is almost equal to 1. I will draw somewhere over here. Okay, and for 100 and for 500 and for 1000, for all that, the values are almost equal to 1. So this is how I'm going to mark it. So in other words, the graph that you're going to get is somewhat like this. That is a curved shape. A curved shape that goes like this. Okay, so this is how we draw the magnitude response. Now let's talk about the phase response. So phase response means, again, we need to look at the equation. So the f of j omega is equal to omega by root of, no, omega by j omega plus, let me see, the complex number you got was j omega by 10 plus j omega by j omega plus 10. Okay, so here, let me write it, j omega by 10 plus j omega. Okay, so how to take the phase angle? You see, when you see a division, it has to be replaced by subtraction. Okay, the phase angle of the numerator minus the phase angle of the denominator. That's how you do it. So what is the phase angle of the numerator? You see the a plus jb, right? So what is the phase? What is the phase of this complex number? It is tan inverse b by a. Okay, but here the real part is equal to 0, or here the value of a is equal to 0, so it will become tan inverse b by a. So which means here it will become, for the numerator it is tan inverse b is omega by, and the real part is 0, so omega by 0. This is the phase angle of the numerator, right? minus the phase angle of the denominator, and the phase angle of the denominator is tan inverse b by a. B is omega, a is 10, so it is tan inverse omega by 10. Okay, tan inverse omega by 10. So what is tan inverse omega by 0? That is nothing but tan inverse infinity. Tan inverse infinity minus tan inverse omega by 10. And what is the tan inverse infinity? Tan 90 degrees infinity. So which means tan inverse infinity is 90 degree. So it is 90 degree minus tan inverse omega by 10. This is the phase angle of f of j omega. Okay, so like this, you need to plot the phase response with different values of omega. That's all. So for that also, again, you take, so here this is how do you can represent like the theta of omega. Okay, this is the phase angle. Theta is a function of omega, right? So theta of omega. So how to represent the phase angle? Same thing. Just draw the graph. Okay, and let me draw another graph like this, like so. And then I'm going to mark the values of 10, 100 and 1000 like so. And then I'm going to mark the value. This is okay, I didn't mark a 0.1, but that's okay. Maybe I just put a mark like this to show that there is a 0.1 also over here. Okay, so here also I'm going to mark 0.1. This is 0.2. This is 0.3. This graph is a rough work. Okay, if you want to draw an actual graph, you should try it on a semi-log paper. Okay, then you'll understand. So this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. That's how it goes. But this is actually in terms of not magnitude, it's terms of angle, right? So angle means it has, you don't write 0. It's actually, you can write it like this. It's 10 degree, 20 degree, okay, 30 degree. It's not a magnitude, right? It's angle. So 30 degree, 50 degree, 60 degree, okay. Then it goes to 70 degree, 80 degree, 90 degree, and so forth. Okay, it goes and it keeps on increasing. Or you know what, let me just draw it in another way. Okay, let me just draw it in another way. You know what, I think the best thing to draw the phase angle is by looking at the graph, by looking at the values of the answer. You see, what is the value? That is, let me write it. That is theta of omega is equal to 90 degree minus, what is the equation? 90 degree minus tan inverse omega by 10. Let's plot the values and then we will decide what should be the range. Okay, I think that is the best way. Let's plot the values and then we'll decide what should be the range. So here again, let me plot it, omega, right? So different values of omega, I'm going to try is 0. I'm going to try 5, then 10, then 50, then 100, then 500, then 1000. That's it. Okay, this much values. And here theta of omega, let me just try for each and every value. Let's see what I'll get. Okay, first is 0. So tan inverse 0 is actually nothing but you will get 90 degree itself. Am I correct? You will get 90 degree itself, right? So tan inverse 0 is 90 degree, which means the highest value won't go more than 90 degree, I believe, right? It won't go more than 90 degree. So this graph was more than enough in that case. Anyway, so 90 degree. Okay, next is 5. Let me see, let me write it over here. So you'll get, let me see, before doing this, don't forget you need to change the mode of your calculator to degrees. Okay, that is how do you do it is you simply take shift setup and then you take the angle unit and then you shift it to degree. Okay, that's how you change it. Make the calculator in degree mode. Or if you're using radians, then you should replace 90 degree with pi by 2. Okay, replace 90 degree with pi by 2. So here it is, how does it look like? It is 90 minus, okay, tan inverse 5 divided by 10, right? 5 divided by 10. This is how it looks like. So you will get 63.43. Okay, 63.43 degrees. 63.43 3 degrees. Next is 10. So let me simply replace this value. So 90 degree minus tan inverse 10 by 10. Okay, you will get 45 degree. So this is 45 degree. Okay, fine. And what next do you have? Next we have is 50. So 90 degree minus tan inverse 50 is 50 by 10, and you will get 11.31 degrees. 11.31 degree. Next is 100. So it will be 90 degree minus tan inverse 100 by 10, and you will get 5.71. So here it is 5.71 degrees. See, the degree is getting small. The phase angle is getting smaller and smaller. Next we have is the 500. So it is 90 degree minus tan inverse 500 by 10, and you will get 1.146 degree. It's getting smaller and smaller. 1.146 degree. And next go for 1000. And for 1000, it is 90 degree minus tan inverse 1000 by 10, and you will get 0.573. 0.573. Let's see what happens for 10,000. Okay, just out of my curiosity, let's try it. So in that case, it will be 90 degree minus 10,000 divided by 10, and you will get almost equal to 0.057 for 10,000. Let me just write it. You will get 0.057. So now we know the range, right? The range goes like 90 degrees. So 90 degrees is the maximum. So I want to know the 90. That's why I just redraw the graph again. So it is 0. How to write 10, 20, 30, 40, 50, 60, 70, 80, 90. Yeah, okay, that's more than enough. So let this be, let this be 5, let this be 10. Since I'm using a lot of space, let me utilize all the space. 10. So in that case, let this be 500, let this be 1000, and after that let this be 500 or 5000, then let this be 10,000. Okay, there, plenty of graph to draw. So here the values will be, like I said, 10, 20, 30, 40, 50, 60, 70, 80. Let me just extend the graph and let this be 90. Okay, 90 degrees. Right, that's it. So this is what you call as the phase response, theta for omega, and this is omega. Okay, so here if it is 0, it's 90 degree. Let's mark it. There's this point. I will use another pen so that you can see, all of it you can see easily. I'm using a dark red pen. All right, this is 90 degree. Next is 5 is 63.43. That is somewhere close over here, right? Let's mark this point, very close to 60. Okay, that's this point over here, right? Okay, so this is the graph you get. Right, next is 45 degrees. For 10 it is 45 degrees. So let this be 45 degree right here, exactly in the middle. Okay, 45 degree. So it goes like this, and then 500. No, sorry, after this is 100. I forgot to mark 100, right? I forgot to mark 100. Maybe I'll mark 100 in between. I'll mark 100 somewhere in between, or maybe I'll just change the value. This is 100. This is 100 means this has to be 500. Then this has to be 1000. Then this has to be, yeah, that's it, 1000. I'll just mark till 1000. Okay, no need to mark this. Yeah, much better. So this is 100. So 100 is 5.71. 5.71 is, this is 10, this is 5, so 5.7 is somewhere in between over here. 5.71. This is for 100. For 500 it is 1 point, which is again it goes down, and for 1000 it again goes almost equal to 0. It goes almost equal to 0, which means your graph will be looking somewhat like this. That is, it goes like this and it goes down like this, right? It goes like this and it just goes in this shape. Okay, it goes somewhat like this, I think, somewhat like this. This is how the graph you get. Okay, better to draw with a pencil, and then so you can get a clear idea how the graph looks like. If you want to get a very accurate graph, then you can put more values into omega and calculate those values in order to get a more finer graph. Okay, So this is how we find the magnitude and phase response. Okay, another let's do one more question maybe based on this magnitude and phase response. So in that case, let us do another problem. So here let f of s is equal to s plus 10 by s minus 10. Let's do this question. S plus 10 and s plus 10 by s minus 10. So here the first thing you do is you just replace s with j omega. So f of j omega. F of j omega is equal to j omega plus 10 by j omega minus 10. Okay, next what you do is you calculate the magnitude and phase response. Okay, I will find both. So here the magnitude response is f of j omega, and this is can be written as, so you know how to write the omega of this, right? This is the numerator can be written as root of a square plus b square divided by, and here also, yes, this is the conjugate. This is nothing but the conjugate of the numerator, right? So here the value is no need of j. So this is the magnitude 10 square plus omega square, and here the denominator is also, it is again it is 10 square plus omega square itself, right? So both the numerator and denominator are same, which means the value is equal to 1. Yeah, for magnitude response the value is equal to, which means the magnitude response of this function is nothing but a symbol value, a symbol 1. That's all. This is the value of the this is the magnitude response of this function. Okay, okay, this is the magnitude response of this function, because you see, because both the magnitude of the numerators, you see here the complex number is 10 plus j omega, here the complex number is minus 10 plus j omega. So when you are trying to find the magnitude response, but in both the case, here it will become, how it will become 10 square plus omega square. The other one is nothing but minus 10 the whole square plus omega square, right? So in both this case also, it does, the values is exactly the same, 10 square plus omega square itself. So when you cancel each other, you will get 1. Okay, root of, yeah, root of, and you will get 1. So that's what happened over here. Okay, so this is not conjugate actually, it's the real part became minus. That's it, right? So that's what happens here. So now next let's do the phase response. I hope the phase response is also easy like this. Phase response, how do you find it? By using the function that is the phase angle of the numerator minus the phase angle of the denominator. So which means here, that is, let's say theta of omega. Okay, theta of omega is equal to, what is the phase angle over here? What is the tan inverse over here? Tan inverse over here is tan inverse imaginary part by real part. Imaginary part is omega, real part is 10, so omega by 10. Okay, minus the tan inverse of the denominator, that is minus tan inverse of, now the imaginary part by real part. Imaginary part over here is omega, and the real part is minus 10. Oh, the real part is minus 10. Okay, the real part is minus 10. This is the equation. You can also write this equation as tan inverse of omega by 10 minus tan inverse of minus omega by 10. If you want, you can do this calculation using this expression for different values of omega. The other way of doing is, you already know that tan and tan inverse are all what are odd function. Odd function means if you see a minus sign at the argument, you can take that minus sign outside. Okay, that means the odd function. So which means here this tan inverse minus omega 10 is actually nothing but tan inverse of omega by 10 minus of minus tan inverse of omega by 10. You can write like this, okay, since because tan inverse is an even function. If this is very difficult for you, you can simply use this expression for plotting the phase response. Okay, this is for my own convenience. So here minus of minus is plus, so you'll get tan inverse omega 10 plus tan inverse omega by 10, which is nothing but 2 tan inverse omega by 10. Okay, so this is your phase response, that is theta of omega. The phase angle of f of s is the phase of f of s is theta of omega is equal to 2 tan inverse omega by 10. So now you need to do is plot the graph for different values of omega using this expression. Okay, so as usual, first let me draw the different values of omega. So I don't know what is the range of my angle, that's why. So here let me say 0, then I will write here 5, then 10, then 50, then 100, then 500, then 1000. Okay, if I need to go more than that, I'll just say from the angle I can say whether I should go more than that or not. So theta of omega. So theta of omega is equal to, let's try it. So what is the equation? What was the equation I got? Theta of omega is equal to 2 tan inverse omega by 10, right? So theta of omega is equal to 2 tan inverse omega by 10. Okay, so let's do this calculation. So you'll get 2 shift tan inverse omega by 10. So first number is 0. So 0 means tan 0 is nothing but 0 degree, right? So this becomes 0. So it means it is 0 degree. Okay, when omega is equal, so because it is tan inverse 0, tan inverse 0 is 0 degree. Next is 5. Let's do for 5. So you will get tan inverse 5 divided by 10. Okay, and you will get 2 tan inverse 5 divided by 10, and you will get 53.13 degree. 53.13 degree. Next is 10. So I'm going to say 2 tan inverse 10 by 10, and you will get 90 degree. Okay, so I think it goes greater than 90 degree. Okay, the next is what, 10, right? No, I just did 10. Next is 50. So 2 tan inverse 50 by 10. 2 tan inverse 50 by 10, and I will get 157.38. 157.38. Okay, next is 100. So I will say, let this be 100. So 2 tan inverse 100 by 10, and I will get 168.58. 168.58. So I think the maximum degree is 180. Okay, next is 500. So 2 tan inverse 500 by 10, and I will get 177. Yes, it's so 180 degrees is the highest number. 177.771 degree. Okay, and for 1000, 2 tan inverse 1000 by 10. 2 tan inverse 1000 by 10, and you will get 178.85. 178.85. Okay, let's see for the 10,000 again. 2 tan inverse 10,000 by 10, and you will get 179. Let's try that one. Almost 180. So that is the highest, right? 179.89 degree. This is almost equal to 180 degree. So this is how we need to plot it. So this time the graph goes in the exponential increment, right? It increases exponentially. Let's draw the graph. So here the graph is like this. As you draw the y-axis. So how to draw means, I think you need to use how to 90 degree, 180 degree, right? So let this be 180 degree. Okay, let this highest number be 180 degrees. So the half of it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5. Let this be 90 degree. In that case, let this be 45 degree. Okay, and then let this be half of it. So let this be 90 degrees. So what is it between 180 and 90 degree? It is 135 degree. 135 degree. Okay, and then in that case half of this should be 45 divided by 2 is 22.5. So let this be 22.5 degree, and over here it should be 22.5 plus 45. Let me see, it is 67.5. So let this be 67.5 degree, and this is 90 plus 90 plus 22.5 degree, and you will get 112. This be 112.5 degree, and this is let me see, 135 plus 22.5, and this is 157.5. Between this is 150. This is more than enough. 157.5 degree. You see, what I did is that I actually looked at the graph values, and then I determined my values of the y-axis, so that you will get a more cleaner graph. Okay, that's all. This is theta of omega. This is 0. This is 5. This is 10. This is 50. This is 100. This is 500. This is 1000. Okay, and then if I get it, I'll make it over here, right here, and make it 180 degree. So how does the graph look like? If it is 0, it is 0. Okay, If it is 5, it is 53.53 means somewhere over here, middle value over here, right? I put mark it over here, 53.13, and for 10 it is exactly 90 degree. This one, okay. So it goes like this. 50, it should be 157, which means 157.38, which is almost equal to over here, right? Almost equal to over here. Okay, so this is the graph you get. And then for 100 it is 168, almost equal over here. And for 500 and all, it goes nearer and nearer, much more nearer to 180, much more nearer, like that. It goes up to 180. So which means the graph is somewhat like this. Okay, the graph is somewhat like this. This is the graph. Okay, and this is how we graph. Of course, if you draw it in a natural graphical paper, you'll get a more beautiful graph. Okay, here I am just estimating the points with respect to its space. Okay, so my graph will never be accurate, right? So this is the kind of graph you'll get, a kind of a curved nature, right? This is the graph, this is the phase. This is how we mark the phase response. The most important thing, more than the graph, the most important thing is how to plot the values, alright? So how do you do that is simply, first you replace S with j omega, and then you replace the complex number at the numerator and the complex number at the denominator with its corresponding magnitude. So like that you'll get the magnitude expression, and like that you can plot the magnitude response. And likewise, when you when you want to plot the phase response, simply find the tan inverse of the that is, you find the phase angle of the numerator, that is the angle of the phase angle of the numerator, and the phase angle minus the phase angle of the denominator. That is tan inverse b by a of the numerator minus tan inverse b by a of the denominator, and like that you'll get the phase angle of the expression. And then you can plot the phase response by looking for different values of omega. Okay, so this is how we plot the magnitude and phase response. Okay.